So hello everyone. Welcome to another episode of Deep Dive Knowledge Talk. Welcome. Today we explore continual learning, teaching models like new data, without forgetting old. We'll discuss catastrophic forgetting like a stability plasticity trade-off, and its three scenarios: class, domain, and task-incremental learning shaping future AI. What are the fundamental principles of continual learning, and how do they address the challenges of training models on a continuous data stream while minimizing catastrophic forgetting so?
Continual learning is like teaching a child new things like every day while making sure they don't forget what they learned before. The main principles revolve around two really important ideas: stability and plasticity. Stability is like a strong tree trunk that keeps the tree standing tall. It actually represents the model's ability to hold on to what it has learned in the past. Plasticity, on the other hand, is like the branches of the tree that can grow and change as new leaves or new knowledge. So come in. So the challenge is to find a balance between these two, keeping the old knowledge stability while also allowing the model to learn new things, plasticity. So when models train on a continuous stream of data, they actually face a problem called catastrophic forgetting. This is like a child who when learning a new subject, forgets everything they learned in the previous subjects. In the context of continual learning, this happens when the model's old knowledge is overwritten by new information. So, to address this challenge, the model can use task-specific output layers. So, imagine a school where each class has its own teacher who just specializes in that subject. This way, even if the main teacher, the shared backbone changes how they teach, each subject task still retains its own knowledge through its whole specific teacher. This really helps to minimize forgetting because the model can learn from new data while still keeping the old knowledge intact. In summary, continual learning focuses on balancing the ability to learn new things while not losing the old knowledge, which is so crucial for the model's performance when tested on all the tasks it has seen before.
So, could you explain the three common scenarios in continual learning as outlined in the study, particularly highlighting how they differ in terms of complexity and the approaches used to really mitigate catastrophic forgetting?
There are three common scenarios in continual learning, each with its own level of complexity and different ways to handle the challenge of catastrophic sort of forgetting. One, class-incremental learning. So this is like the most challenging scenario in SOLDA. So every new portion of data introduces completely new classes that the model hasn't seen before. Just imagine a car driving from a city to the countryside. In the city, it recognizes pedestrians and buildings, but when it reaches the countryside, it really encounters animals and trees that are entirely different. The model needs to learn to recognize these new classes while still just remembering the old ones. To mitigate forgetting in this scenario, the model has to carefully adjust its weights to accommodate new knowledge without losing exactly what it has already learned. 2, domain-incremental learning. This scenario is a bit easier than situational. So the model doesn't change its output head, which means it keeps the same way of responding to tasks. Instead, it learns to adapt to different domains that might have the same classes, but could look so different. For example, a model may actually learn to recognize dogs in both a park and a beach setting. So, since the output head remains unchanged, so the model can focus on adapting its understanding without worrying too much about forgetting the previous knowledge. 3, a task-incremental learning like this is the easiest scenario in task-incremental learning. Each task has its own separate output like heading. Think of it like a student having different notebooks for each kind of subject. The student can actually write down everything they learn in each subject without mixing them up. This separation helps the model to retain old knowledge so easily because it doesn't have to overwrite anything. Each task keeps its information safe and sound. In summary, as we move from class-incremental learning to task-incremental learning, the complexity decreases, and so does the risk of catastrophic just forgetting. Each scenario has its own strategies to maintain balance between learning new things and retaining old knowledge.
So what methods or techniques are really commonly employed in each of the three scenarios to effectively manage the stability plasticity trade-off and prevent catastrophic forgetting during the learning process?
In each of the three scenarios of continual learning, so different methods are used to manage the stability plasticity trade-off and prevent catastrophic forgetting. One, class-incremental learning system. Since this scenario is the most challenging, methods often involve careful adjustments to the model's parameters. Techniques like regularization can be used, which is like putting a safety belt on the knowledge the model already has. So this helps to keep the old information stable while allowing the model to learn new classes. Additionally, techniques such as selective retraining may be applied, where the model revisits old tasks to reinforce its memory and ensure it doesn't forget what it has actually learned. Two, like domain-incremental learning in this scenario, so the methods focus on maintaining the same output head, which simplifies the learning process. Techniques such as knowledge distillation can be employed, where the model learns from its previous versions or teachers like, this is like a student learning from their past exams to do better in future tests. By using the knowledge from earlier tasks, the model can adapt to new domains without losing the understanding, like it gained from the previous ones. 3, task-incremental learning. Since this is the easiest scenario, the separation of tasks allows for simpler methods. So, each task has its own output head, so the model can retain old knowledge without really significant risk of forgetting. Techniques like task-specific training can be used where the model focuses on one task at a time, ensuring that it learns really well without interference from other tasks. This is similar to a student studying one sort of subject thoroughly before moving on to the next one. In summary, so while class-incremental learning requires more complex methods to keep old knowledge stable, domain-incremental learning uses knowledge from previous tasks to adapt, and task-incremental learning benefits from the separation of tasks to minimize forgetting. Each scenario has tailored strategies to balance the need for stability and plasticity effectively.
What implications do the findings of these scenarios have for the future development of machine learning systems, particularly in terms of real-world applications, where continual learning is essential?
The findings from the 3 scenarios of continual learning have really significant implications for the future development of machine learning systems, especially in real-world applications where ongoing learning is essential. 1, adaptability to changing environments like class-incremental learning, which deals with entirely new classes of data, is crucial for applications like self-driving cars. As these vehicles navigate different environments, so they need to recognize new objects and scenarios without forgetting previous knowledge. This adaptability ensures that they can operate safely and effectively in diverse conditions, enhancing their reliability. 2, efficiency in learning domain. Incremental learning allows models to adapt to new environments or contexts without significant changes to their core structure. So this efficiency is valuable in areas like healthcare, where models must learn from new patient data or treatment protocols over time. It just means that systems can stay up to date with the latest information without needing to be retrained from scratch, saving time and resources. 3, task specialization. Task-incremental learning emphasizes the importance of keeping tasks separate, which can lead to really better performance in specific applications. For instance, in customer service chatbots, having distinct models for different types of inquiries can actually improve response accuracy. This specialization allows for a more tailored approach, leading to better user experiences. Overall, the insights from these scenarios encourage the development of machine learning systems that are more flexible, so efficient and specialized. As real-world applications increasingly require systems to learn so continuously from new data, these principles will guide the design of smarter, more capable models that can thrive in dynamic environments.
How do the findings regarding catastrophic forgetting in these kind of scenarios inform the ongoing research and development of techniques aimed at enhancing the longevity and robustness of machine learning models in practice?
The findings regarding catastrophic forgetting in the whole different scenarios of continual learning provide valuable insights that shape ongoing research and development in enhancing the longevity and robustness of machine learning models like 1, understanding the stability plasticity. Trade-off research just continues to focus on finding the right balance between stability and plasticity. By recognizing that catastrophic forgetting is a significant challenge, so developers can create techniques that allow models to retain old knowledge while still being flexible enough to learn new information. This understanding drives innovations in model architectures and training methods that prioritize both aspects. So, 2, task-specific output. Layers like the findings highlight the effectiveness of using task-specific output layers to minimize forgetting. This approach informs the design of future models, so encouraging the use of separate components for different tasks. By doing so, models can learn and adapt without compromising previously acquired knowledge, so leading to more robust systems that perform well across various tasks. For selective modification of shared components, the research indicates that catastrophic forgetting can occur when the shared backbone of a model is modified too much. So this insight leads to the development of techniques that allow for selective adjustments to shared components. So ensuring that essential knowledge is preserved while still enabling the model to adapt to new data. This kind of targeted approach enhances the model's longevity and effectiveness over time. For continuous learning from new data, as models are trained on continuously arriving data, the need to retain knowledge from old tasks just becomes even more critical. Ongoing research aims to create methods that facilitate this retention, ensuring that models can really evolve without losing their foundational understanding. The focus on continuous learning is absolutely essential for applications where data changes rapidly, such as in finance or healthcare. So in summary, the findings on catastrophic forgetting inform the development of techniques that enhance the durability and adaptability of machine learning models by addressing the challenges of retaining knowledge while learning from new information. So researchers can build more robust systems that perform reliably in real-world applications.
What kind of future research directions or emerging techniques show promise in further mitigating catastrophic forgetting, particularly in the context of class-incremental learning? Given its complexity,
future research directions and emerging techniques that show promise in mitigating catastrophic forgetting, especially in the context of class-incremental learning, so include several innovative approaches. One, regularization techniques, like researchers are exploring advanced regularization methods that help maintain stability in the model's knowledge by applying penalties to changes in important parameters. These techniques can really protect the learned information from being overwritten when new classes are introduced. So this approach is akin to putting a protective layer around valuable knowledge to keep it safe. To memory augmentation, incorporating memory mechanisms into learning models can help retain information about previous classes. This could involve creating a system where the model can remember key features or examples from earlier tasks, just allowing it to reference this memory when learning new classes. Think of this as a student keeping a diary of important lessons to review when studying new subjects, like through dynamic architecture adjustments, developing models that can dynamically adjust their architecture as new classes arrive is actually another promising direction. So this could mean adding new neurons or layers specifically for new classes or keeping the existing structure intact. This flexibility allows the model to expand its capabilities without losing exactly what it has previously learned. For task-specific adaptation, focusing on creating task-specific adaptations where the model can fine-tune its parameters based on specific characteristics of new classes can also be pretty effective. So this approach ensures that the model can learn and adapt to new information without compromising its existing knowledge base. Self-supervised learning. So utilizing self-supervised learning techniques can help the model learn from unlabeled data, enhancing its ability to generalize from previous tasks while incorporating new information. This method encourages the model to find patterns and relationships in data, which can reduce the risk of forgetting. In summary, these emerging techniques and research directions aim to create more robust systems, capable of handling the complexities of class-incremental learning. So, by focusing on maintaining stability while allowing for adaptability, so researchers can develop models that perform better in real-world applications where continuous learning is essential.
So thank you all for joining us for this insightful discussion. It's always been fascinating to delve into the world of continual learning with our esteemed researcher. As we've explored today, continual learning is a crucial area focused on enabling models to learn from endless streams of data while skillfully combating catastrophic forgetting. So that kind of challenge, where new information can unfortunately erase old knowledge. At its heart, CLAL strives for a delicate balance between stability, retaining what's already known, and plasticity, the capacity to adapt and acquire new skills. So we've seen how this manifests across different scenarios, from the intricate complexities of class-incremental learning, where entirely new categories emerge, to the more manageable domain-incremental settings, adapting to new contexts while maintaining output structure. And finally, the task-incremental approach, which with its separate output heads, provides a simpler path to continuous acquisition. So the path forward. So as we've discussed, points towards enhancing this critical stability-plasticity trade-off. So future advancements will likely involve innovative memory augmentation, dynamic architectural adjustments, precise task-specific adaptations, and the power of self-supervised learning. All of these efforts are geared towards one vital goal: developing more robust machine learning systems that can actually truly learn continuously and thrive in the ever-evolving real world. A big thank you again to our guests for sharing such valuable insights, and to you, our audience, for being with us. So we hope you'll join us for our next deep dive into the cutting edge of technology. Until then, take care.